topic is discrete frequency spectrum. Before I talk on this topic, discrete frequency spectra, let me remind you the complex form of the Fourier series, which is given to you as this one. It is actually the exponential form of the Fourier series, and it is the complex form because it involves an iota in its form. Before that, the trigonometric Fourier series is actually the real form of the Fourier series, or you can say real form, and this is the complex form. And where the Ck are the complex coefficients. These are the complex coefficient which is given to you as 1 over t. It's now 1 over t, not 2 over t, over the whole period. X naught to x naught plus t means over the whole period. It might be 0 to 2 pi, 0 to pi, minus pi to pi, whatever. F of x e to the power minus iota k omega x. Omega is the frequency which is equal to 2 pi over t, and iota, you can see iota over here, and k is from 0 plus minus 1. K can take negative values as well. Where in the real form of the Fourier series, which is actually the trigonometric Fourier series, we have k varies from 0 to infinity. For k 0, we have only a naught because b naught is equal to 0, and all the coefficients a, k, b, k are real, and that is a real form. So in general, these coefficients are complex and they can be expressed as every complex number can be expressed as its in the polar form as its the radius or its distance, or you can say r or rho from the distance from the 0, the point, the distance from the 0, and the argument phi k is the argument. So here the Ck magnitude is actually equal to Ck conjugate, and this is in turn equal to this one. So this Ck, 2 times of Ck is called the amplitude of the kth harmonic, right? Amplitude of the kth harmonic, and phi k is related to the phase of the kth harmonic. So now we are going to derive another form, the third form, the last form of the Fourier series, which is the compact form or the Amplitude-Phase form. So what we do in this form, we have this trigonometric Fourier series, which is given as this one, and we suppose this a naught equal to a naught over 2 equal to the capital A naught, and this coefficient equal to ak cos of phi k, and bk equal to this minus ak sine of phi k. So why I'm taking it minus ak sine phi k, because I can then apply the sum formula to it. So while then putting the values ak equal to this one, then I will get f of x is equal to, this is now a naught plus summation ak is ak cos phi k and cos k omega x minus ak sine phi k and sine k omega x. Now this becomes a naught plus, I can take ak common, and now this is my cos phi k cos k omega x minus sine phi k sine k omega x, which is equal to cos of k omega x plus phi k. This. So this is the compact form. You can see a compactness because there is only a cos of angle involved in it. When you open it, you get this value in this. So k is from 1 to infinity. So this is the compact form of the trigonometric Fourier series, this series. So now what are ak or these coefficient, and what are psi k? So in this compact form, the term a1 cos of omega x plus psi 1 is called the first harmonic or the fundamental mode, and it has the same frequency omega as the parent function of it. We have seen that the frequency of the function is omega, so this omega has the same frequency. The term ak cos of k omega x plus psi k is called the kth harmonic, and it has a frequency k omega, which is k times of the fundamental frequency. That is, this is actually the frequency of the kth harmonic. This whole term is called a kth harmonic, and this is k omega, we call it as frequency of the kth harmonic. So omega k is equal to k omega, means 1 is equal to the original frequency of this function f of x. Omega 2 is equal to 2 omega, omega 3 is equal to 3 omega, and so on. So this is the breakdown of this the Fourier series into the harmonics or modes. Similarly, we can substitute this instead of writing it ak cos phi phi k, I can substitute ak equal to sine phi k and bk equal to this, so that I can apply the sine formula over here. In this case, I will get this thing, and by compacting it, this I will get this in terms of the sine. So this is the compact form or alternate amplitude phase form. This one is the alternate amplitude phase form. Why it is called amplitude phase form? Because this AK is the amplitude of the kth harmonic. It denotes the amplitude of the kth harmonic, and this phi k, which is equal to this one. You could see what is my AK. I can find AK from here by squaring and adding these two equations. I can squaring and then adding AK square plus BK square is equal to, I can take AK square common, and in the middle I would have cos square phi plus sine square phi k, which is equal to 1. So it is equal to this one. And similarly, dividing this equation with this one, that is BK over AK, I have minus sine phi k over cos phi k, which is equal to tan minus tan phi k over bk over ak. So phi k is equal to minus, I can take minus here. So phi k is equal to tan inverse of minus bk over phi k is the phase angle, measure the lag or the speed of the kth harmonic with reference to the pure cosine wave of the same frequency. It's the pure harmonic cosine. This is the term of the cosine. So we have this one. And for the alternate amplitude phase form of the Fourier series or alternate compact form of the Fourier series, we have this sine form of the frequency. So the term, this is called the first harmonic or fundamental mode, and it has the same frequency as the parent function. And this term is called the kth harmonic, and it is k times the that of the fundamental frequency. And again, the amplitude expression is the same, while the phase angle now changes into this one, which is reference to the pure sine wave of the same frequency. Sine value के case के लिए you have this formula for the phase angle. So why we are finding the compact form or the amplitude phase form of the Fourier series? Because we want to find the Fourier spectra or the frequency spectrum of this waveform. So let's see the connection between, we have seen so far, we have seen the three forms of the Fourier series. The first one, which is the trigonometric Fourier series, TFC, then the complex Fourier series, and then the amplitude phase form. So we know the relationship between the real and complex Fourier series. A naught over 2 is equal to C naught, and CK is equal to AK minus iota BK over 2, and minus, and we have only minus difference in the minus sign. And A naught is equal to this one, AK is this one, and BK is equal to this one. Also, you can, by adding and subtracting these two equations, you get this relation in the second line. So to develop the amplitude phase form of the trigonometric Fourier series, we used these expressions. For the first one, cosine waveform, and this one is A naught is equal to A naught over 2, AK is equal to this one, and the phase angle is equal to tan inverse, so minus BK over AK. So this is the relationship or connection between all the three forms of a Fourier series. Okay. Okay. So now let's see what is discrete frequency spectra. So in expressing a periodic function by its Fourier series expansion, we decompose the function into its harmonic or frequency components. So if f of x is a periodic function of period t pi, then its frequency components at frequency omega k is equal to 2k pi over t, which is k omega, right? So these are the frequency components. So हमारे पास जा रहे थे सारे frequency components, where omega is the frequency measured in radian per second of the parent function. So you have this relationship, frequency components. So a Fourier series may therefore be interpreted as constituting a frequency spectrum of the periodic function f of x and provides an alternate representation of the function to its time domain waveform. The frequency spectrum is often displayed by plotting the graphs of both the amplitude and the phases of the various harmonic components against the angular frequency omega t. So frequency spectrum is the plot of amplitude against the angular frequency omega k, and the plot of phase angle against the angular frequency omega k. The plot of the amplitude against the angular frequency is called the amplitude spectrum, while the plot of the phase angle against the angular frequency is called the phase spectrum. So this for a periodic function of period t, harmonic components only occur at discrete frequencies, omega k. So the graph of the spectra or the plot of these amplitude spectrum and phase spectrum both are considered as the discrete frequency spectra or line spectra or discrete frequency spectra, because what we do, we plot this. This is my angular frequency omega k, which is equal to k times omega. And this is my amplitude ak. And also, if you could see this, what is the relationship between this? Because also I have the amplitude is also given as this one, 2 times this. So this is 2 times ak. Or ck is equal to ak divided by 2. That is ck is equal to this over 2. So if I take the values omega k, for example, like this is omega naught, omega 1, maybe this is omega 2, omega 3. Similarly, if I draw these values of the amplitude, these are like line spectra or the discrete frequency spectra. And similarly, I can draw this for the phase angle, and I get the different values of the angular frequencies. So I get a phase spectrum. So discrete frequency spectra consist of amplitude spectrum and phase spectrum. So there are two types of discrete frequency spectra, as you can see, one-sided and two-sided. This is one-sided and this is two-sided. And this is two-sided phase spectrum. So what is the difference between one-sided and two-sided? So a plot of AK against angular frequency will constitute the amplitude spectrum, and that of phi k is equal to this one against omega k angular frequency will constitute the phase spectrum. So the spectrum, discrete spectra obtained in this way is now known as one-sided discrete frequency spectra. Why it is one-sided? Because here we have for the compact form, the values of k are 1, 2, 3 up to so on. So omega k is equal to k omega, that is omega 1 is equal to this, omega 2 is equal to 2 omega, omega 3 is equal to 3 omega. So omega lie only on this frequency is positive. So this positive multiple of this frequency is also positive. So this lies on one side of the x-axis, or you can say this is my omega k, and this is the amplitude. That's why this is one-sided. And if I plot the coefficient ck, take the coefficient of the complex Fourier series, which is actually this one, magnitude and amplitude of the spectrum. The amplitude spectrum is the plot of this ck against omega k, and the phase spectrum that of the phi k against omega. Because here I have to draw ck, and here for the complex Fourier series, they are negative values as well. The values of k are negative. So omega, I have values omega 1 is equal to plus minus omega, omega 2 is equal to plus minus 2 omega. Positive values are plotted here and negative values are plotted here. Because omega k is equal to k omega. Two-sided spectrum. In this case, it is known as two-sided spectrum. Okay, let's solve the question. The question is this, that is, you are given a periodic function which is defined by g of t is equal to e to the power minus t over 2, where t varies from 0 to pi, and this pi is a periodic function with a period of 2 pi, that is t is equal to this pi. And first we have to sketch the graph of g of t. And then second part is obtain the trigonometric Fourier series, compact trigonometric Fourier series, that is the Amplitude-Phase form, and sketch one-sided discrete spectra. The third one is find the complex Fourier series and sketch two-sided Fourier spectra. So how to plot the Fourier, this function first. So we are going to plot this function, or a function, to know that what is the graph of an exponential function g of t is equal to g prime telephone, which is e to the power t over 2. If I draw simply an exponential function with this positive argument, this is my exponential function. It crosses the y-axis at this point. So this is f of t, and this is t. This is the graph of the exponential function. Now I have to draw g of t the power e minus t over 2. So e minus t over 2 is the reflection of this graph along this axis, like this. This is the reflection. So this is the graph of e to the power minus t over 2, right? But I have to take it from 0 to pi and then add it. So 0 से 2 pi, 0 से pi तक जितना ये ग्राफ बन रहा है. So 0 से pi तक इस ग्राफ को इंसर्ट करेंगे. थोड़ा सा इसको जूम कर देते हैं कि यहाँ लाइक करें. So this is my pi, this is 0, this is g of t, this is t. So 0 से pi तक का ग्राफ. And again we will repeat the same law because it has a period of pi. So I will repeat it. Same pattern this 3 pi. ये रेप्लिका हिस्ट्री के साथ इसको नेगेटिव साइड पे भी प्लॉट कर सकते हैं. सो दिस इज द ग्राफ ऑफ दिस फंक्शन, दिस पीरियोडिक फंक्शन. ये मैंने e की पावर t over 2 और e की पावर माइनस t over 2 के प्लॉट किया. और ये आपके पास ग्राफ इसका ग्राफ ये है. ठीक है. तो इसके बाद हमें करना है ट्रिग्नोमेट्रिक फोरियर सीरीज विद कॉम्पैक्ट ट्रिग्नोमेट्रिक फोरियर सीरीज एंड स्केच वन साइड डिस्क्रीट स्पेक्ट्रा. इसको करना है और इसमें अब मुझे थोड़ा सा चाहिए होगी थोड़ी सी स्पेस. आई नीड I will so I have done the first part. Now comes the second part, which is the trigonometric Fourier series and the compact Fourier series and the sketch one-sided. Okay, so let's start the first part. We have done the first part. So this is trigonometric Fourier series. So my function is g of t is equal to e to the power minus t over 2, where t lies from 0 to pi. So what is my time, this period t? Here we will say it is t naught. So you can represent it t naught or with t also. So this and omega naught or omega, which is also omega, is equal to 2 pi over t naught. T naught is pi, so this is equal to 2. So trigonometric this Fourier series is given as g of t is equal to a naught over 2 plus summation k cos k omega t. Now omega is equal to 2, so I have 2 kt plus bk sine of 2 kt. This k is from 1 to infinity, where a naught is equal to 2 over t. T is pi over its integration over its period, which is 0 to pi, and f of t, that is g of t minus t over 2 and dt. So I will integrate it. 2 over pi is a constant. Integration of t to the power minus t over 2 divided by the coefficient of its exponent, coefficient divided by its coefficient of its exponent, which is minus 1 by 2. I have to divide it with minus 1 by 2. So it becomes minus. So this is pi, this is 0. So here it becomes 4 over pi with a negative sign Okay, let's put it over here. And this is e to the power minus pi by 2 plus 1. And if I calculate it, e to the power minus pi by 2, it's not e to the power minus iota pi by 2, it is simply e to the power minus pi by 2, which is a real number. So I get 1.008. This is my answer. So what is my AK? AK is equal to 2 over pi.
Excuse me, ma'am.
Yes,
अब
yes,
मैम यहाँ पे सेकंड लास्ट स्टेप में e raised to power pi by 2 minus 1 नहीं आएगा?
yes, it's minus 1. Sorry. Thank you. But the answer is 1.008. Okay, so here I could write it as 2 over pi iota because I have to apply the integration by parts again and again. So what is my I? I is equal to 0 to pi t minus t over 2 cos of 2 kt dt is equal to. So now I have to apply the integration by parts. Let's take the cos of 2 kt as the first function and e to the power minus t over 2 as the second function. I will also take e to the power minus t over 2 as the first function because it's more easy if I take cos 2 kt as the first function. So this becomes first function as it is, integral of the second function minus 2, then integral from pi to 0 minus 0 to pi, derivative of the first function, that is cos of 2 kt minus sine 2 kt multiplied by 2k, integral of the second function minus t over 2 into minus t dt. So when I substitute this value, the limits of integration, I will get minus 2 cos of 2k pi e to the power minus pi by 2, and then plus 2 cos of 0 e to the power 0, then minus 3 minus becomes minus 2 into 2 4 k integral of sine 2 kt into e to the power minus t over 2. Again, I have to integrate it by parts. So the integration by parts, first function as it is sine 2 kt, integral of the second function pi to 0 minus derivative of the first function cos 2 kt into 2k, integral of the second function 0 to pi. This. Now this is minus 2. This function cos of 2k pi is 1, always equal to 1, minus 2 e to the power minus pi by 2, and this is plus 2. So this is, when I substitute pi over here, I will get sine 2 k pi, which is 0, and when I put 0 here, I will get sine 0, which is 0. So in this case, this becomes 0. So minus and this minus and this minus. Again, I have a minus sign over here. This 2, 4, and this 4. This becomes 16 k, and this k is square. And in the integral, I have the integrand is cos 2k pi 2kt e to the power minus 3 over 2, which is I, this one. So here I get 1 plus 16k square I. I can take this 2 common from here, which is 1 minus e to the power minus 5 over 2. And this implies that I is equal to 2, 1 minus e to the power minus 5 over 2 over 1 plus 16k square. So what is my AK? My AK is 2 over 5. 2 over 5 means 4 over 5. Multiply with this 4 over 5. 1 minus e to the power minus 5 over 2. 1 plus 16k square. This one. And then I will get, if I calculate 1 minus e to the power minus 5 by 2 multiplied by 4 divided by 5. This is the same value, this one. So this is 1.008 over 1 plus 16 case. Okay. So on the same lines, we will calculate Vk. Vk is equal to 2 over pi 0 to pi e to the power minus 3 over 2 sine of 2kt dt. So again, you will apply integration by parts and solve it, and then you will see that your answer is, I have calculated it. Okay, my Vk is 4k 1.008 over 1 plus 16k square. And when I multiply 1.008 with this 4, I get 4.032 over 1 plus 16k square into k. This is my Vk. So my trigonometric Fourier series becomes g of t is equal to 1.008 divided by 2 plus summation ak. AK is this 1.008 over 1 plus 16k square cos of 2kt plus 4.032 over 1 plus 16k square sine of 2kt. This one, k is from 1 to infinity. So when I divide it 1.008 with 2, I will get 0.504. So here I can take this common 1 plus summation from k1 to infinity. I'm just simplifying it a little bit. 2 over 1 because this 0.504 is 2 times. This 1.008 is 2 times 0.504. 16k square cos of 2kt. I have k as well. Plus this 4.032 is 4 times 0.504, 8 times this. So already I have taken this one. 4k sine of 2kt in this and this. So this is my trigonometric Fourier series. Now I have to calculate the compact or the what is this compact TS, compact form of the trigonometric Fourier series or amplitude phase form of the Fourier series. So for amplitude phase form, I know that A naught is equal to A naught over 2 which is 0.4504, and AK is equal to AK square plus BK square, this one, and this is, here's my AK and where's my BK. I can take 0.504 common, 4 over 1 plus 16K square plus 64K square over 1 plus 16K square, this square. So AK is equal to 0.504, taking the LCM, which is 1 plus 16K square whole square, and here I have 4 plus 64K square. I can take this 0.404 common from here, becomes 2 after coming out of the square root, and in the special inside the square root I have 1 plus this 16K square, which is cancelled with this one. So I have this expression, which I would write rather as 2 over 1 plus 16K square. So this is my AK. And what is my phase angle? This is tan inverse of minus BK over AK is equal to tan inverse of minus 4K, which is minus tan inverse of 4K. So my compact form of the trigonometric series is G of t is equal to A naught 0.504 plus, I can take this common, and summation from K1 to infinity 2 over 1 plus 16 K square, this thing, and then cos of 2KT plus psi k is minus tan inverse of 4K. So this is my compact form of the trigonometric Fourier series. So in order to draw the discrete frequency spectrum, one-sided or two-sided, I will make a table. Remember that one-sided discrete frequency spectrum and my frequency components are omega k is equal to k omega, omega is 2, so this is 2k, which known, these are known. K is from 0 to infinity, so it is 0, 2, 4, 6, 8, so on. That is, I can take values A0, 1, 2, 3, 4. So my frequency, my components are these are 0, 2, 4, 6, 8. So I have to plot angular frequency component against this AK. This I will instead I will take the CK, This is 0.504. 0 point, substitute different values in it. The AK, this is my AK. Zero point 244, 0.125, 0.084, 0.063, and then the angle cycle. This angle, which is this, substitute different values of K, 0, 1, 2, the inverse of 0 is this is minus 75.963. This is minus 85.26. Minus 86.42. Minus 81.1. So first I will plot the one-sided amplitude spectrum. Omega K on this side and AK on this side. Bye, Allah Hafiz. AK and AK at 0, AK is 504. At 2, the value is 0.244, which lies between this line and this line. This is simply a graph of amplitude against the angular frequency, AK against omega t. This is 4, and this is the half of it.
Excuse me, madam. मैडम कहना है ये मैं कहना चाह रहा था कि आज हमारे यूनिवर्सिटी में जुम्मा एक ही होगा, तो आप काइंडली अटेंडेंस ले सकते हैं अभी?
जी मैं अटेंडेंस डाउनलोड कर लूँगी, अटेंडेंस डाउनलोड हो जाएगी। If you want to leave, you can go. तो 1 बजे जुम्मा में लिखा है। तो दिस इज द ग्राफ। बेसिकली ये आपके पास ये लाइंस बनेंगे, आपने इसको ज्वाइन नहीं करना, सिर्फ मैं आपको पैटर्न दिखा रही हूँ इसको। ग्राफ जो आपके पास बनेगा वो कुछ इस तरह से। दिस इज द एम्पलीट्यूड, वन साइडेड एम्पलीट्यूड स्पेक्ट्रम। और अगर मैं ड्रॉ करूं दिस फेज एंगल against ओमेगा के, तो ये सारी वैल्यूज नेगेटिव आ रही हैं। 0 पे 0 है, 2, 4, 6, 8 के वैल्यू है 70.9, फिर है 85, थोड़ा सा और आगे this graph, and then I have minus 86, and then 80 वाली थोड़ा सा इससे नीचे. So this is the second, the one-sided phase spectrum of this frequency. Okay, this is one-sided frequency spectrum, and the third part is the complex Fourier series and sketch two-sided Fourier spectra. So now we have to calculate complex Fourier series, which is given as g of t is equal to summation ck t to the power 2 iota kt. dt k is from minus infinity to infinity. So where c k is equal to 1 over pi 0 to pi t to the power minus t over 2 t 2 iota kt dt is equal to 1/5, and I can write it as t minus common, so 1/2 plus 2 iota k t dt, which is equal to 1/5 integral of this t to the power minus 1/2 plus 2 iota k t divided by the same minus 1/2 2 iota k from pi to 0. This is, you take calcium 2, it becomes minus 2/5 into 1 plus 4 iota k. Substitute t equal to pi first. 1/2 plus 2 iota k pi minus e to the power 0, which is 1. So minus 2/5, this is minus 2/5, 1 plus 4 iota k, and this is e to the power minus pi/2 multiplied by e to the power 2 iota k pi. 2 iota k pi is equal to 1 because it is equal to, by Arnold's identity, it is equal to cos of 2 k pi plus sine of 2 k pi. Cos of 2 k pi is equal to 1, sine of 2 k pi is equal to 0, so it is equal to 1 minus 1. So we already calculated this quantity. Minus 2 times this, which is 0.504 over 1 plus 4 iota k, right? So this is my ck. And calculate ck. This is ck, and then I will calculate its magnitude ck, and then I will calculate the this angle phase of k, which is actually the same tan inverse of psi k is equal to, this one is this tan inverse of minus 4k. या आप जैसे कैलकुलेट करेंगे, नाउ यू हैव दिस कॉम्प्लेक्स नंबर, अगर आप कैलकुलेट करेंगे तो आपके पास यही आंसर आएगा. दिस इज योर ck, and if you calculate its magnitude, you will get the same this answer. So then you will plot the two-sided spectra. The values are same, only the double of this. Here I will take the angular frequency, and here I will take the ck magnitude, which is at 0, it is 0.504. At this, it is half of a के over 2 का हाफ ही है बेसिकली, तो ये यहाँ पे आ जाएगा जो हमने वैल्यू कैलकुलेट की थी 0.2414 डिवाइडेड बाय 2, और दूसरी ये 2 के ऊपर ये वैल्यू है, 4 पे वैल्यू है 0.125 डिवाइडेड बाय 2, ये जो भी हमने यहाँ कैलकुलेट 25 डिवाइडेड बाय 2, दूसरी बात की आ जाएंगे. अब इस पर इसमें फर्क ये है कि ये नेगेटिव साइड पे भी वही वैल्यूज आपने प्लॉट करनी है, क्योंकि के नेगेटिव भी है तो ये नेगेटिव साइड पे इसका मिरर इमेज भी बन जाए. सो दिस इज द एम्पलीट्यूड स्पेक्ट्रा. और उसके बाद अगर हमें फेज एंगल करना है तो फेज एंगल आपके पास ये है, फेज एंगल स्पेक्ट्रा. दिस इज साई के अगेंस्ट फ्रीक्वेंसी इक्वल्स टू 4 6 -2 -4 -6. Okay. When I take the negative, when I substitute a positive, I will get negative angle. That is, एंगल सारे वही होंगे जो यहाँ पे आपके पास आए हैं, प्लस और माइनस, ये जितने एंगल यही हमने प्लॉट करने हैं. एक्सेप्ट कि अगर k नेगेटिव होगा तो ये माइनस और माइनस प्लस होगा। तो यहाँ आपके
मैम
पास
जुम्मे
जो
के टाइम हो रहा है।
ठीक है बच्चे जाए आप, बस ये मेरा थोड़ा सा रह गया। इन अदर वर्ड्स यू वांट टू से दैट वी स्टॉप टीचिंग तो ज्यादा होगा। एक क्वेश्चन ही बस किया आज, और नेगेटिव साइड पे ये पॉजिटिव वैल्यूज का ये ग्राफ बनेगा, दिस इज द ग्राफ। So this is how you draw the two spectra, one for the one-sided discrete spectra, one for the amplitude, and the other one for the phase spectra, and two-sided के लिए you take the complex form of the Fourier series, और इसमें आपके पास वही चीज है। So you have one more question to solve. So try these questions. I will hopefully upload the solution on the slide as well. Just try the solution or try to type the solution so that you can get it on the slides. Yes, any question?